Yeah, hello everyone. It's our pleasure to have Ioannis over here to share about his new work, random natural gradients. Um, yeah, everyone know that optimizing a PQC is pretty hard to do, and now, Ioannis methods might provide us a new way to do the optimization more efficiently, and it is our great pleasure to have him here to share about um his work. And yeah, just now actually Ioannis shared the link GitHub page for the code over here that utilize random natural gradient to do the optimization. So if you are interested, you can go and check it out. Ioannis, the floor is yours.
So, first of all, thanks very much for the invitation. I'm going to introduce myself. My name is Ioannis Kolotouros. I'm a final PhD student at the University of Edinburgh. Currently, I'm doing my residency at Sandbox AQ for 7 months. Then I'm coming back to Edinburgh to finish my PhD. Today, I'm going to talk to you about random natural gradient, a classical optimization method that we developed very recently. I hope that you will like it and you will start using it as well. So, okay, perfect. So in today's talk, I'm going to give you a small motivation on our idea and our method. I'm going to give you a small introduction on variation of quantum algorithms, which I'm pretty sure most of you know really well. I'm going to tell you about a very interesting optimization tool called the quantum natural gradient that came out some years ago. I'm going to discuss the quantum and the classical Fisher information matrices, and then I'm going to introduce two optimization methods that we developed. And then finally, I will end my talk with a small discussion about future work. So, as you probably already know, we are currently in the NISQ era where the quantum computers that are available are small in size, they are noisy, their connectivity is limited, and the coherence times are small. This means that this poses the question on whether these devices can be any useful, if they can provide any valuable outcome. To address these questions, people started and developed hybrid quantum classical algorithms where the quantum computer generates quantum states that cannot be classically simulated by a classical computer, and the classical computer post-processes and the quantum computer measures these states as well, and the classical computer post-processes these measurements in a hope for a practical advantage. The question, however, of whether this framework can provide any practical quantum advantage is still open. One of the things that I'm going to discuss here today is when we are searching for a practical quantum advantage, we should be really careful on how we distribute the quantum and classical resources. For example, if you have an optimization algorithm that uses a linear number of quantum states, but requires a quadratic memory, quadratic classical memory is much different than a classical optimization algorithm that uses quadratic number of quantum states, but then the classical resources are linear. So we must be really careful on how we distribute these resources. Now, this variation on quantum algorithms, I'm going to give you a small introduction on how they work. Actually they are pretty simple. You're given a mathematical problem that you want to solve, and what you're doing is you map this problem into a Hamiltonian whose ground state is actually corresponds to the solution of your problem. So this Hamiltonian can be decomposed as a sum of Pauli terms, which scales as a polynomial to the system size of qubits. Then what you do, the user selects a parameterized family of gates in the quantum computer with again a polynomial to the system size number of parameters, and initialize the parameters of the quantum circuit at random. Then what you do, the user executes this quantum circuit. It measures the parameterized quantum state, and with this measurement, the classical computer then post-processes these measurements and calculates some objective function. Not only the objective function, but sometimes its derivatives, its higher order derivatives, its Hessian, and so on. So If you want to check, 2 years ago, we published a paper called Evolving Objective Function for Improved Variation Quantum Optimization, where instead of using the expectation value of the Hamiltonian as the loss function, we used a thing called ascending CVAR, where it's really useful if you're trying to solve a combinatorial optimization problem. So someone can even choose a different objective function, not use the loss, that will improve its results. Now, the step 5, which is the most crucial for this paper, is that once you have this the values of the loss function or its gradients, the classical computers employs a classical optimization algorithm and updates the parameters towards the direction that minimizes the loss. For example, here I have the equation of the gradient descent, which is really simple. What you do is you calculate the gradient of the loss function, and you move by a small step size towards that direction. Then what happens is that you iteratively do this loop, this continuous feedback loop between the quantum computer and the classical computer until you have converged to a minimum. And then if you have then you have a ground state approximation, and so our approximation of the solution that you try to solve. Of course, as you all know, although this framework looks really promising, it has lots and lots of problems that we still haven't solved. The first thing is that the loss function landscapes is highly non-convex. So local optimization methods usually converge to a local minimum, which is highly dependent on how you initialize your parameters. Sometimes you will have good convergence, sometimes you have a bad convergence. On top of that, you have the barren plateau problem, which means that as the number of parameters increase and the number of qubits increase, and you start at random, it's highly likely that you will fall in a plateau, which means that the gradient of the loss function goes exponentially to 0, which means that if you want to even move in the landscape, you would have to use exponential number of measurements so that you will know in which direction to move. And finally, what we would like to state is that the classical optimization algorithms that people use most of the time, I'm going to talk about quantum natural gradient in a few seconds, like gradient descent, Kobila, SPSA, this type of algorithms treat the quantum computer as a black box, which means that you're only taking information about the loss function, its derivatives, its higher order derivatives, but you're not looking at the state and how the state changes. So there's an extra information there that you can actually exploit and be really useful. The thing is that you have to exploit it fast and not in order to be practical. Now, there is this very interesting optimization method called the quantum natural gradient. In the first equation, on the first line, we have the gradient descent. Now, what Stokes and his collaborators thought, they said, okay, they were inspired by a method called natural gradient, which comes from the classical literature, and they said that we can actually update the parameters by considering what change is happening in the quantum state, in the underlying quantum state. So what they actually did is they preconditioned the gradient of the loss function by the inverse of the quantum Fisher information matrix. I'm going to tell you in a few seconds what the quantum Fisher information matrix is, but this method works pretty well. Sometimes it avoids local minima, but the problem with this approach is that it is impractical, as if you have m number of parameters in your quantum circuit, then you would need to prepare m squared quantum states. And not only that, in order to calculate the elements of the quantum Fisher information matrix, if your circuit that generates a quantum state psi of theta requires a depth d, then in order to calculate the elements of the quantum Fisher information, you need twice the depth, which is really bad for current quantum devices. Now, what is a quantum Fisher information matrix? The quantum Fisher information matrix is a matrix in the space of parameterized quantum states. Consider the distance between two parameterized states, psi of theta and psi of theta. Sorry, psi of theta prime. Then the infidelity is defined as equation 5. The interesting thing is to understand what's happening when your two parameterized states are really close one to the other. So one quantum state is parameterized by the parameters theta, and the other quantum state is parameterized by the parameters theta plus epsilon, where epsilon is a small shift vector. And then one can show that the distance between these two quantum states can actually be written as 1/2 epsilon transpose the quantum Fisher information times epsilon, which means that if you calculate the quantum Fisher information matrix at the point theta, then you can actually understand, you can do in your classical computer, you can understand how the quantum state changes by putting small epsilons. So the quantum Fisher information actually quantifies how your quantum state changes if you change certain parameters. So it's a very useful tool, as we will see in the next few slides. Let's discuss why it is so important. The first reason, it comes from a very nice paper called Capacity and Geometry of Parameterized Quantum Circuits. And if we do this really small analysis here, I'm telling you it's really simple. If you consider the distance between these two states, the distance between the state psi of theta and psi of theta plus epsilon, and you consider the eigenvalue decomposition of the quantum Fisher information matrix, because it's a symmetric and real matrix, then if you go to equation 9, suppose that you move this parameter epsilon goes towards the direction of the alpha A eigenvector, scaled by a very small scalar mu. Then one can show that the distance between these two quantum states is actually lambda I/2, where lambda I is the eigenvalue of the quantum Fisher information of the AI eigenvector times mu squared. This is really important. This means that when the quantum Fisher information has small eigenvalue, this means that if you change the parameters towards that direction, your quantum state doesn't change much. Now, if the eigenvalue towards that direction is really large, that means even if you change the parameters by a small amount towards that direction, your quantum state will change significantly. So the quantum Fisher information really tells us that how if we change certain parameters, how the quantum state underlying are changing. So a very illustrative example is this 1-qubit example. Consider the most general 1-qubit state, this psi of theta, phi, which is cosine theta/2, and so on. If someone goes and calculates the quantum Fisher information matrix, it's really simple. If you do it, you will see that it's this matrix down on the left. It's diagonal with one eigenvalue being 1 and the other eigenvalue being sine squared over theta. To give you a geometric understanding of what that means, if you go to the North Pole, to the state 0 here, and even if you change the parameter phi at that point, your quantum state won't change. So you have a singularity at that point. You have a point where even if you change the parameters, nothing happens to the quantum state. Now, if you think this happening in a more high-dimensional landscape, this is what happened in the parameterized quantum circuit. You have certain points where even if you change parameters, nothing really happens to the quantum states. So this paper is really good. Okay, now that we have an understanding on what the quantum Fisher information is, let's move to understand the quantum natural gradient. So as we said, we have the vanilla gradient descent, which is just update the parameters towards the direction that minimizes the loss. Now the resources that are needed are you only have to do the time of the quantum state that you have to prepare scales linear with a number of parameters. Sorry, this is not a capital M, this is a small m. I'm gonna fix it, don't worry. And the classical resources that you need is also scales also linearly with a number of parameters. And because you have to save the vectors in your classical memory. On the other hand, the quantum natural gradient, you need m squared quantum resources that scale as a quadratic to the number of parameters. And also you need quadratic to the number of parameters classical memory to store the matrices. So intuitively, now that you understand what the quantum Fisher information is, what the quantum natural gradient does is when your quantum state changes by a small amount, you're making large steps towards that direction. But if your quantum state changes by a lot in that direction, you're making your parameters change only by a small amount. So you're putting information of the quantum states in your update rule. And that's what makes it an information theoretic method. And another thing that's we also prove it in our paper as well is that the quantum natural gradient provides the steepest descent direction, which means that if you take the first order Taylor expansion of the loss function, it becomes a minimum if you do this update rule. Now, just as we discussed distances in the space of quantum states, someone can define distances in the space of probability distribution. A natural choice of distance measure for the quantum states was the infidelity. Now, a natural choice for distance measures in the space of probability distribution is the KL divergence, or else the relative entropy, which is defined as you see in equation 13. But how do you get probability distributions in the quantum setting? Of course, by performing measurements. So what you're doing is you prepare a quantum state, you choose a measurement basis M, you measure, and then you get a probability distribution. Of course, by measuring a quantum state, the amount of information that you get is highly dependent on the measurement basis that you have. Now, let's consider these two parameterized quantum states, the psi of theta and psi of theta plus epsilon, where epsilon is again small. Let's suppose that we measure both of these states, and we get the probability distribution with respect to the measurement basis M. If we do the same analysis as the quantum Fisher information matrix, then we can see that the KL divergence can be written in the exact same form as the infidelity of the quantum states, where instead of the quantum Fisher information matrix, we now have the classical Fisher information matrix because we were working with probability distributions. It's really what is really surprising is that in order to calculate the classical Fisher information matrix, you don't need m squared quantum resources, but you only need linear to the number of the number of parameters. So you have a quadratic advantage when you calculate the classical Fisher information matrix, but of course carries less information than the quantum Fisher information matrix. Now, what we define in our paper is the optimal measurement, and we define the optimal measurement in a way that it gives you the maximum information about the changes happening in the quantum state if you perform a measurement. So so we define the optimal measurement as that measurement that if you calculate the KL divergence between these two quantum states that change by a small amount, it will maximize the distance. So actually a different way to express equation 15 is also equation 16, which means that we can define the optimal measurement as a classical Fisher information matrix that minimizes the norm, that its distance from the quantum Fisher information matrix. Actually, there are some really nice papers that actually discusses on whether such a measurement exists, where the classical Fisher information matrix is actually equal to the quantum Fisher information matrix. Of course, even if it's not exactly the same, if you're still close, then you're pretty happy. Now, one of the things that we show is that in order to calculate, let's suppose that if you choose your measurement basis by first applying a global unitary, to rotate the quantum state, and then measuring the computational basis. In that case, if you want to find the optimal measurement, that means the measurement that will give you the most information about what's changes happening about the changes happening in the quantum state, then you will have to solve this optimization problem in equation 17. This problem is non-convex and it's very hard to solve. So it's not a good strategy to in an optimization problem to go and find the optimal measurement and then use this measurement to update your parameters with a natural gradient. You have to be more clever, because solving equation 17, it's really hard and requires a lot of quantum resources. What we actually found, which is pretty interesting, and we're trying to prove it theoretically as well, is that we can get much information about what changes happening in the state space by performing random measurements. So what we found is that if you choose a hardware efficient ansatz at the end of your quantum circuit and perform this random unitary and measuring the computational basis, we saw that as you increase the expressiveness of this random unitary that you rotate your quantum state and then measuring, we saw that it approximates the optimal measurement. So instead of solving this optimization problem, you're still approximating by introducing randomness in your quantum circuit. And we propose the update rule in equation 18. I'm going to give you more into going to explain to you what's happening in a few seconds. So instead of preconditioning the loss function by the quantum efficient information matrix, the inverse of the quantum efficient information, we preconditioned by the inverse of this classical efficient information matrix, where we chose the measurement at random. Now, this is super useful because the number of quantum resources that you need scale is linear with the number of parameters. So you have a quadratic advantage, but you still have some error in your calculation because your classical efficient information still differs from the quantum efficient information matrix, which in practical cases you don't really care. It's if it works well and you get information about what's really happening, then you're happy. And the classical sources that you need scale is quadratic with the number of parameters because you still need to store the matrix. Now, to explain to you how we perform the random measurements and to help you understand is that you have a quantum circuit that generates a quantum state psi of theta, and then at the end you append an extra quantum circuit at random. You do a random rotation, and then you measure in the computational basis, and then you get a bunch of probability distributions. And with these probability distributions, you can actually calculate the classical efficient information matrix, which is really simple. Now, if you see these plots here, we compare the random natural gradient that you can see in the orange line compared to the quantum natural gradient, which is the green line, and gradient descent, which is the blue one. On the left side, we see the optimization iterations until convergence. Optimization iterations means how many times you change your parameters in your quantum circuit. And on the right hand side, we see the actual quantum states that one has to prepare during the optimization process. As you can see, the number of quantum states that you have to prepare, and even the optimization iterations, are significantly less than the one needed in the quantum natural gradient. If some of you have ever worked with the quantum natural gradient, you will have seen that if you go above 12 qubits, things are really hard to simulate. So it takes too much time to even do one simulation. Now, with our method, if you start working with it and playing with it, you will see that you have a really fast convergence in a matter of minutes compared to the quantum natural gradient. And the other thing is that, as you can see, the gradient descent is the one that performs really bad in these cases because it doesn't take information about the changes happening in the quantum state. Now, this figure shows that we actually played. We said, okay, let's instead of using this random global unitary that we first shift the parameters then measure in the computational basis? What if we don't measure in the computational basis, or if we don't measure in a Pauli basis? We saw that this doesn't work because the Pauli measurements do not encapsulate the information that it's hidden in the quantum state. So you're missing a lot of information, which makes your optimization not converge. So as you can see here, the classical natural gradient with measurements on the Z basis performs really bad. It's actually doing random moves and never converges. The other method that we developed, it's called the Stochastic-Coordinate quantum natural gradient. As we already discussed, some of the bottlenecks of the quantum natural gradient is that it requires too many quantum states to prepare during the optimization. For example, there was a very recent paper by some people from IBM, I believe. They showed that if you have a quantum circuit with 600 parameters and you perform 100 iterations of the quantum natural gradient, you would need 1 year to converge, which, as you can see, you can't hope for a quantum advantage if you need 1 year to converge if you select this type of optimization method. The other thing that is a bottleneck in the quantum natural gradient is that if you go and calculate the quantum efficient information matrix, that you will see that its rank, or the number of zero eigenvalues, is very large. So there is a lot of directions which do not change the quantum state. And the other thing is that because there are parameters that what's actually happening is that there are parameters where if you change them, the same type of changes will happen in the underlying quantum states. So the thing is that you have a large redundancy on the parameters. So it would be ideal if you knew which parameters lead to independent changes in your quantum state. The thing is that at different parameter settings, different parameters matter. So, for example, in one iteration, some of the parameters will change the state in a different way. Then in the next iteration, some other parameters will change the state independently, and so on. So we were inspired by stochastic coordinate methods from the classical literature, where instead of optimizing all of the parameters in your quantum circuit, you can actually sample at random a subset of the parameters and then optimize only this subset. Of course, we took it a bit further and we said, okay, what if we calculate the reduced quantum efficient information, which is the quantum efficient information only on that subset? And we saw that we defined the reduced quantum efficient information matrix as the element ij of the reduced quantum efficient information is the element of the quantum efficient information ij if both the indices I and j are on the subset that you want to optimize. If it's not, then the value is 0. 1 second, So in this lemma, I'm not going to go into details, but what it says is we quantify the probability of if you have a subset. So let's say you sample you have a parameterized quantum circuit with m parameters, and you sample at random only L of them, where L is smaller than m. And let also the number of independent parameters being L, sorry. Let the number of independent parameters, being L, and the number of parameters that you sample being L plus K. Then we quantify the probability that we actually sample all of the parameters that independently change the quantum state, and it's this quantity in equation 20. So finally, you can see in equation 21, we can introduce our method, which is called the Stochastic-Coordinate quantum natural gradient. So at only iteration, we only look at a subset of the total parameters. We calculate the reduced efficient information for that subset. and we update the parameters with this update rule. Of course, this reduces the number of quantum resources to L squared because you're only looking on L parameters instead of M, and the number of and the classical memory that you need scales also as L squared because you're only considering this dimension for the matrices. Finally, let's put everything together to see how these three methods perform one compared to the other. We can see that the random natural gradient is the best out of these three. The blue one, which is the stochastic-coordinate quantum natural gradient, we have to state here that one, during the optimization, have to actually decide how many parameters they want to sample at random. So this is a hyperparameter that we haven't optimized, so one needs to play with it as well. In our case, what we said is okay, at every iteration, let's look only half of the parameters. So we're gonna randomly sample half of the parameters of the quantum circuit, and we're gonna optimize only this half. And at every iteration, we uniformly sampled half of the total parameters. And as you can see, while it needs more optimization iterations to converge the stochastic-coordinate quantum natural gradient, the actual quantum states that you need to prepare is much smaller. So even it's more practical, the quantum natural gradient. And these figures correspond to max cut instances of three regular graphs of 10 qubits. Finally, the take-home message here is that we should actually rethink the classical optimization part in variational quantum algorithms. What we should do is make the classical part more quantum. The classical computer must take as much information as possible from the quantum state with clever ways during the optimization. The other thing is that we must find more sophisticated methods to sample the subset of parameters in this in stochastic-coordinate quantum natural gradient or in other stochastic-coordinate methods in variational quantum algorithms. And finally, there is the notion of overparameterization in quantum information matrices, and there is also where in variational quantum algorithms we know that when you overparameterize a quantum neural network, sometimes you get some really nice properties. It's really interesting to see what happens when we have overparameterization of the classical information matrices, which happens in a different, which happens much sooner than the quantum information matrices, and to see if this has any advantage during your optimization. Thanks a lot. You can find the paper on the archive. You can find our code on GitHub. Feel free to play. Feel free to ask me whatever you want. That's it.
Cool. Thanks, Ioannis, for the very interesting talk. For the audience, if you have any questions, feel free to unmute yourself to ask the questions, or just type the questions in the chat that I could help you ask about it. In the meantime, I could ask a couple of questions. Could you go back to your first figure? Just want to make sure that I understand your result correctly.
This one or the other one?
No, the one with a distribution.
This one?
No, the one before. This one.
This
yeah.
one.
Yeah. So
yes.
yeah. So how you so you just like say you have a V of 5, right? And then you just randomly choose the 5. And for each 5, how many measurements would you be doing over there? Is it just one shot measurement and then you move towards the other basis, or you would choose multiple measurements for a single basis? Like how do you do that?
Okay, let me explain. So here, so everything in my simulations is exact. So I have the exact state vector in all of my experiments. So what you do here is that for every point in the histogram is a different type of measurement. So let's go to the right one on the Pauli measurements. This every point here corresponds to a different Pauli measurement. So we have the quantum state that we are at the moment. We performed a Pauli measurement. For example, it could be a measurement on the Z basis, on the X, on the XY, and so on. For X on one qubit, Y on the other qubit. That's what I mean. And you construct the classical Fisher information matrix for that type of measurement. Well, if you perform Pauli measurements, if you go and calculate the classical Fisher information matrix, you will see that its distance is very far away from the quantum Fisher information matrix. As you start introducing entanglement in your unitary before your computational basis measurement, you start to approach the quantum Fisher information matrix. And the more entanglement you put and the more randomness you put, you start and you calculate the classical Fisher information matrix, you start to approach even more the quantum Fisher information matrix. So that's what happened. And especially so for example, for the first layer here, what really happens is that you put an ansatz family with of one layer, some bunch of rotations in each qubit, and some entangling gates between the qubits. And what you do is you uniformly sample at random the parameters of this hardware efficient ansatz. And you do this for a bunch of times. Now, for example, in the 9 layers, you put 9 layers of that thing, and you uniformly sample at random the parameters of this hardware efficient ansatz. And if you go to the nine layers, no matter what type of parameters you put in your hardware efficient ansatz, your classical Fisher information matrix will always be close to the quantum Fisher information matrix. So that's what it means here. So you're getting yes, exactly.
Yeah, so then the question now would be how the short noise or the hardware noise affect the efficiencies of this type of optimization method. Do you have any ideas of how that would be?
That would be a good thing to explore, actually. I haven't done it yet.
That
would be interesting.
For hardware noise, okay, that may be a part because it's pretty hard to study. I'm just like a bit curious of the short noise, like how short noise will affect the optimization, because like typically if you want to kind of like estimate the Fisher information, we have to do measurements and then compute the KL divergence and stuff, right? So on that note, basically, like if we restrict the number of shots, for example, to 1, there are a lot of bases that we are not seeing. So there will be a kind of minimum threshold that we have to put and stuff like that, right? If I'm not, yeah. So I would see like short noise would play a very, very important role over there. And just wondering how the number of shots will be scaling with the number of qubits that you have, because like over here it seems like it's quite kind of independent of the number of qubits for your scheme. It just depends on the parameters. But yeah, just wondering whether like the short noise would have the short numbers would have to do with the scaling of the qubits or not. Yeah, that would be a kind of interesting things to see.
Yes, exactly. I agree. And you know, the thing is that if you go and calculate the quantum Fisher information matrix, and when you do in a practical scenario, you will calculate each element independently. You will still have an error in your entries. You would still have to calculate the inverse, and sometimes if you have this small error in your entries, your inverse can be affected too much. So you have to play a lot on how you calculate the inverse. So there are ways to calculate the inverse, and so you must be really careful if you want to make these things work. If you go in a case where you have actual measurements to calculate each entry, so you have to be really careful.
Right.
Sometimes you have to neglect some things in order to make these things work. So it needs a bit of further optimization.
Right. Yeah, because I'm just thinking that whether it's like how would the short noise be affecting like this particular graph, right? Whether it will broaden the spectrum or lowering down or something like that. So it's kind of like good to know.
That would be interesting, yeah.
Yeah, because like that's one thing that find is quite different compared to the classical variations or probability distributions is that we can control the barren of the variable that we are interested to estimate, right? So we can control the number of shots, and how would that be affecting the optimization you'll be interested for? We have the one question from the audience. Do you calculate the exact quantum nature gradient, or do you use a diagonal/block diagonal approximation?
I use the exact QNG in this case. You could use the block diagonal. The block diagonal has the problem that if some parameters that correspond to different blocks are highly correlated, this approximation makes no sense. That's the problem with that approximation. So if you have guarantees that some parameters corresponding to different blocks are independent one with the other, then you are fine on using the block diagonal approximation. I've done some experiments with the block diagonal approximation, but I haven't put anything on my. It doesn't really work that well sometimes. I have made some analysis in the paper. You can really look is that if you have a positive semi-definite matrix, most of the times you will go towards a descent direction. So if you precondition your loss function by a positive semi-definite matrix, then you always go down. You always go downhill. The thing is that your positive semi-definite matrix must have some intuition about what's happening in the quantum state. You can't just put any positive semi-definite Hessian matrix that might make no sense. So for me, the diagonal approximation sometimes corresponds to a positive semi-definite Hessian, to a positive semi-definite matrix, but does not have any physical intuition. So it just happens that it works well. Sometimes it won't. Hope that I helped.
Okay. So another question that I have over here is on, okay, of course, like this beyond the scope of your paper, but just curious your thoughts about that, because over here you use that hardware efficient ansatz, right? To kind of increase, to increase the randomness or the correlation between the measurements and stuff like that, so that it's closer to the quantum feature information. But typically, what we kind of really do like nowadays is to kind of take the symmetry into account. And like, do you see any kind of do you expect any improvement if we kind of like consider like not hardware efficient ansatz, but the kind of quantum circuit that's constructed by underlying symmetries of the data? Like, would you expect some kind of improvement over there, or do you think it's worth trying?
Well, I can tell you what I'm working on at the moment, which is that we're not using hardware efficient ansatz. We use that for that paper, but we're playing a lot because we are simulating molecules at the moment. We're playing a lot with this chemical parameterized quantum circuits called UCC, UCCSD. And things are working pretty well there as well. So we're gonna put an update probably in a month or two. We're doing some things with it with this kind of stuff as well. So this method, this method actually, it's very close to a thing called imaginary time evolution, if some of you know. And imaginary time evolution is a classical algorithm. So you evolve the state not according to the unitary evolution e to the minus th for a time-independent Hamiltonian, but you consider a new type of variable, it, you consider it as tau, and you apply this non-unitary operation. Now, how you can do this in a quantum computer, there are some ways that you can do it. And this type, our method, the quantum natural gradient is actually the same thing as the imaginary time evolution. And so our method is very close to the imaginary time evolution as well. The thing is that with the imaginary time evolution, you have some guarantees of converging to the ground state if some conditions are met. One of the conditions is that you must initialize your parameters in a way that you have an overlap with the ground state, even an exponentially small, you don't care. And the thing is that of course, your ansatz family must be expressive enough so that it reaches the ground state at the end. So if these conditions are met, you have some guarantees that you will go towards the ground state. So we're working on a follow-up thing with this approach, with a connection to imaginary time evolution and how we can simulate molecules. I hope that you will find it interesting as well.
Yeah, yeah, of course. Yeah. So, but how big is the molecule that you guys are considering now? Like all yeah.
Up to 12. I have played up to 12 qubits. I
Okay.
haven't used anything bigger. I will probably. The thing is that sometimes I compare with the quantum natural gradient, which is the limit where things can run on my lab. Even if I go further than 12 with the quantum natural gradient, it won't work.
Yeah, nowadays I think another kind of skill set that we need to learn is to use SPT to do simulation, because like it's hardly for us to go beyond 12 qubits or something like that, right?
That's true. I have a colleague here who is pretty good. Maybe I can convince him to run things on HPC.
All right. Yeah, there's another trick. Yeah, just get to know a colleague there who knows how to do this kind of things. Then just like ask things to him. Okay.
Hi,
okay.
Yanni, sorry. Can I ask a couple of questions?
Yes.
Yeah. So one is on your slide 17. So 2 slides from here.
Okay. See. Yes.
This one, yeah. So for the classical natural gradient with the Z basis measurements, when you say poly Z measurements, how does it look like for general arbitrary random poly strings instead of just poly Z? Is it a little better?
It's the same thing. Sometimes you may find one Pauli matrix that things may work a bit better, but you would still not converge to the point that the quantum natural gradient and the random natural gradient converge. So you would go in a point above. So that's you will go in a suboptimal minimum. You have this kind of problems.
I see. And then for this, for the random natural gradient that you use for this plot, is it so because I saw in previous cases you had like you varied the number of layers. So for this one was how many layers did you use for the Hubble efficient answer?
I don't remember, to be honest. I have to check. I don't remember. Do I state here? No.
Is it one of the largest one, or is it one of the largest number of layers, or it's somewhere in between?
I don't remember.
Okay,
Sorry for I don't remember.
No problem. Yeah. Then finally, okay. So actually, yeah. Okay, I think your answer on UCC answered another question that I had was, I mean, how efficient? I think if you stick to RY, as I understand the conventional hardware efficient one, then basically that as I understand, it's not as generic as if you included RX. Maybe you can't explore the complex space. I'm not sure, but in any case, I think when you explore the UCC ansatz, you probably covered a much bigger Hilbert space.
Yeah.
Anyway, let me just move on to the last question I have is in your last slide. Before the summary, sorry, 2020.
Oh, yes.
Yeah. So for this, I was wondering, do you also consider a metric that is the product of these two metrics? So the optimization iteration times the quantum state preparations. I think maybe that can reveal like a total simulation time taken or required as a metric to compare.
That's a good idea. No, I haven't thought about it. Thanks for that. Yeah, actually, this is a good idea. No. So it's
I think it's relevant in terms of simulations. You will know actually the total, the total time savings or comparing between the methods. Yeah. Okay. That's all I have. Thank you.
Cool. Thanks.
Okay. Yeah. Maybe let me like finish up the discussions by one final question. Like Amira like put out papers on the scaling of backpropagation scaling for quantums, right? Like, do you have any ideas how we can reach that limit? Just some open-ended question.
Sorry, can you tell me the question again? I think
yeah, because recently like Amira Abbas like put out a papers, right? Like basically just trying to see like whether we will achieve like backpropagation scaling for like quantum gradient evaluations and stuff like that.
Yeah, like, I read that paper, yes.
Yeah, in your opinions, like do you see is there any way for us that we can even kind of reach that scaling, or we have to find some other clever way to deal with that? Yeah, just some open-ended questions for you because you are working on this, like you're an expert.
spoiler alert, I'm gonna work on these things in the next few months, so I don't know yet the answers, but I find the question really interesting on how what you can do if you can actually improve the scaling of the calculation of the gradient. To me, that's a very interesting question. So I don't know, maybe we can discuss it together at some point. I'm happy to work with any of you people, seriously. So we can discuss that in the future if you want. I want to go more into the details of what's really happening underneath and whether you can actually, and for what type of circuits maybe we can have a better scaling, the calculation of the gradient, and whether these circuits can actually provide any valuable advantage. So maybe it's, you get some better scaling, but this is what you can do with classical computers as well. So I don't know. It's a very interesting question.
Yeah. So I guess like this is one of the questions that we have to answer. Otherwise, if the training of PQC is not efficient or PQA is not efficient, then it's hardly for us to do anything useful for that, right? Yeah.
Yes. Well, it's still the linear scaling. It's not that bad. It's that it's worse than what we can do in neural networks. But I don't know. Maybe we don't need that many big number of parameters in quantum computers to see something valuable. Maybe we don't need the billions and trillions of parameters that the classical models need to have something useful on the computer. So even if we have a worse scaling, we have a less number of parameters as well. Who knows?
Yeah, is it like I think we really need to kind of try our best to look for the problem that have this kind of properties that's like, okay, it's efficiently solvable on quantum but not for classical. Then on that stage, then like if the joint resources that we need to solve is comparable to the classical one, then we are good, right? Or we can improve it further afterwards. So maybe in the future we will look at kind of like joint cause together instead of just like gradient scaling. We also need to look at the other part of resource scaling and then multiply them together. Yeah. Hopefully like people will go and investigate this. Cool. Thanks again, Ioannis, for the very interesting talk. And I believe people will go and start using that, even the kind of like interesting scaling that we have over here compared to quantum natural gradient design. Okay.
Thanks a lot, guys.
Thanks. Yeah.
See you.
Thank you, guys. Yep. See you.
Bye.